you guys to be as interactive as possible since there's so few of us. If you don't have a problem unmuting yourself to talk, you can ask questions that way or just use the chat. And if you're comfortable turning your video on, that would also be nice, but no pressure. All right. So just a couple of general announcements from our team. We have this $500 goal to register as a nonprofit, which would help us reach more students, and we're pretty close to that goal. So if you're able to, please donate just a couple dollars, but again, no worries if you can't. And then we also have a Facebook study group to join, that you can join to find study buddies on your same test date, or just to find a helpful community to keep you accountable. And then this is our general email, mcat101questions@gmail.com, that you can reach out to us. Like I was mentioning in the chat before, maybe all of you got here, but if you have any questions about just how to get started with studying, or if you have questions on how to put your application together, personal statement help, resume help, you can reach out to us there and we'll help you out as much as we can. Okay, any questions? So these are just the overview topics I put on there that you can refer to if you look back at these slides later, so I won't read them out loud, but there they are. So what is electrostatics? So electrostatic and circuit physics often go together. The difference is that electrostatistics looks at stationary, so non-moving charges, while circuits look at the physics of moving charges. So what is charge? Charge is just a fundamental property like mass, or so it's just a property that certain particles have, and the unit of charge that we use is coulombs. And we have this unit called a fundamental unit of charge, and that's denoted by lowercase e. And the quantity of that is 1.60 times 10 to the negative 19th coulombs. So this fundamental unit of charge is actually the smallest quantized unit of charge. So if you remember light physics, so light is also quantized in terms of photons, which means that the photon is the smallest unit of light that can be broken down into. So similarly, charge is quantized in this form of E. So this value is actually the magnitude of charge of both electrons and protons. So for protons, it's negative E is the charge, and for sorry, did I say that backwards? Electrons is negative E is the charge, and for protons, positive E is the charge. So if you look at that picture on the right, probably something that you're all well aware of, but opposite charges exhibit attractive forces, so they're attracted to each other, which is denoted by these two arrows pointing towards each other, whereas like charges, so two positive charges or two negative charges, are repelled from each other. And another important thing to keep in mind is that charge is always conserved. This means that charge is not destroyed or created, it's merely transferred between all systems on Earth, essentially, which is similar to how mass is always conserved. Okay, so we also have this concept of insulators and conductors, which is what you can think of as all materials in the world being divided into. So insulators are materials that do not easily distribute charge over its surface. So if you look on the left, this material is an insulator, and it somehow acquired a negative charge on one part of its surface. And because it's an insulator, those negative charges stay where they are at and do not distribute evenly over its given surface. On the other hand, you have materials called conductors, which do evenly distribute given charges across its surface. So if you can imagine that, like the insulator, it acquired a negative charge right here, But given that its properties allow it to distribute its given charges over its surface evenly, these charges have spread apart um, into evenly over its surface. So insulators are commonly, or conductors are normally metals and insulators are non-metals. So in this image of this wire here, so the conductor in the middle um, passes electrons along to pass on electricity, whereas the insulator surrounds that conducting material for safety purposes, so the outside surface of a wire doesn't pass along electricity in case somebody touches it. So the first and probably the most fundamental concept in electrostatistics is the Coulomb's law. And what this law and its formula tells you is the magnitude of the electrostatic force that is present between two charged particles. So if you look at this equation and you remember the gravitational force equation, it looks very similar. So the gravitational force in physics is generated between two substances that have mass. Similarly, the electrostatic force is generated between any two substances that have charge. So in this equation, you have K, which is a proportionality constant, which is just a constant that you should memorize for calculations in the physics section. So its value is just 9 times 10 to the ninth. And then you should also memorize the units because they should cancel out the units of these values to give you newtons for force. So, okay, after K, you have Q1, which is the magnitude of charge of the first charged particle. And then you have Q2, which is the magnitude of charge of the second charged particle. And lastly, you have R, which is the distance between these two charged particles. Okay, so this equation gets you the magnitude of the force. So how do you get the direction? The direction of the force is determined by the type of charges. So if you have a positive and negative charge, so these are unlike charges, the direction of the force is such that it's an attractive force. The force will be pointing towards each of the other charges. On the other hand, if you have two like particles, the force is repulsive, so it will face away from the other charge. And the direction, so like the plane, I guess, that the force points along is along the line that connects these two particles. So if you can imagine a line between connecting the center of these two particles, this is like your given plane. So regardless of a attractive or repulsive force, that force will have to point along that line. Okay, I have a practice question here. So if you have a magnitude, so this is a problem calculating electrostatic force. So if you have a magnitude of one charge and it's doubled, what is the ratio of the original value of the electrostatic force to the new value of the electric field? Oh, sorry, ignore that. That should be electrostatic force both times, given that the distance and other charge remains the same. So I'll launch a poll. And you can answer that poll. I'll just fix this one. And I did just change the way, so I put the new value in front, so I think that might have messed up some of your answers because I just realized but the answer in the next slide is for the new value to the original value rather than the original value to the new value. Okay. Okay, I'll go ahead and stop it in a few seconds. So I'll share the results. It looks like most people picked A or B. Does anyone feel comfortable unmuting themselves or putting the explanation in the chat? I'm not sure what happened. Why you can't see it. It's no big deal though. If you want to put your answer in the chat, that works too. Either is fine. Okay, so I'll just go ahead and share the answer. So it's B. So here's the calculation. So when you look at the initial condition, you can see that you have a regular Q1, Q2. So this is our initial condition. And we said that in the changed condition, you have a doubled magnitude of one charge. So we can denote that by saying 2 times Q1. So once you plug that into the equation, you get 2k times Q1, Q2 divided by r squared, which equals 2Fe. So when you double the magnitude of one charge, you double the overall electrostatic force. Any questions on that? And then when you have any answers with square root of 2 for electrostatic force questions, that really only happens when the distance is changed. So when you're changing charges, it'll just be a 1-to-1 change. So like if you double the charge, you get double the electrostatic force. Okay, so the next concept is an electric field. So an electric field is an inherent property of every charged particle. So it's this physical charged field. And what that field does is it exhibits forces on any other charges that move into the space of that field. So we call the charge that is generating an electric field the source charge. And any charges that move into the space of that electric field generated by the source charge is called the test charge. So if you look at the image on the right, we are going to derive essentially the equation for the electric field from the Coulomb's law. And the Coulomb's law, if you remember from the previous slides, show how to calculate the force between two charged particles. So the electric field then you can get by dividing the magnitude of the force between two charged particles by the magnitude of one charged particle. So in the previous slides, we wrote the Coulomb's law a little bit differently. So instead of using Q1 and Q2, we're denoting it as Q and then Q0. It's the same thing, it's just a different way to write it to make the electric field equation a bit clearer. So I have here that Q is our source charge and our Q0 is a test charge. So the charge that you divide by is the test charge, which means, so once you get that divided by Q0, what you're left with is K times Q. So magnitude of the source charge divided by R squared. The test charge is QO. So definitionally, the electric field is generated by the source charge. So the electric field is an inherent property of the source charge. And then the test charge, as we define it, is any charge that moves into the electric field. Does that help, Claudia? Okay, awesome. And I should have made this a little bit clearer. So in the earlier slide, the electrostatic force unit is newtons. So if you take electrostatic force and divide it by the charge of the test charge, that's going to be in coulombs. So the unit of an electric field is in newtons per coulomb. So how do we show the electric field properties? So we use field lines, which are imaginary, but we use that to show the direction that electric field points in. So this is just per convention, so it's not anything that has intrinsic meaning, but conventionally in the study of physics, you draw electric field lines in the direction that a positive test charge would experience. So this is an image of like an electrode plate. So you have one surface that's positively charged and another surface that is negatively charged. So if you were to draw the electric field lines between them, it would point towards the negatively side surface. And this is just convention because if you placed a positive test charge in this space, it would be attracted to the negative electrode. So as a result, if you had a positive source charge and a negative source charge, the electric field lines would point in different directions. So because we are assuming that when we draw electric field lines, it would be for positive test charges, the lines, electric field lines for positive source charges face outwards. And then so that's the opposite for negative source charges because positive test charges would be attracted to a negative source charge. So as I mentioned, field lines are imaginary lines that represent how a test charge would move in the presence of the source charge. And another thing that is important to remember is that field lines that are closer together, so like more densely packed, indicate a stronger field. So this charged particle's electric field is the strongest because it's the most densely packed. It's also useful to think about the fact that in the electric field equation, you can see that the field decreases as the farther you get away in distance. So because R is in the denominator, when R increases, electric field decreases. So visually, you can see that when you're closer to the charge, these lines are more closely packed together, which indicate that the electric field is stronger. And as the farther and farther you get away, the lines spread apart. So the electric field decreases in strength as you move away from the charge. And this is, if that's not confusing to you, that's a good way to remember the relationship between the electric field and distance from the source charge. Okay. And in some cases, you might be wondering, there could be multiple source charges in one space. So to calculate the sum, so like the total electric field at a given point, what you can do is you take the vector sum of individual electric field components. So here you have one positive source charge. So because it's a positive source charge, conventionally the electric field lines point away from it, and that's your vector for that charge, electric field vector based on that source charge. And you have your second source charge, which is negative. So conventionally, negative electric field lines point towards negative source charges. So you have this electric field vector for this source charge and this electric field vector for this source charge. And when you sum your vectors, you get this total line. And I would recommend you guys, if you don't remember how to add vectors, to brush up on that as well. So here is another question. So in the figure below, you have 4 charged particles indicated by spheres Q1, Q2, Q3. And you are told that Q1, Q2, and Q3 are positive, but you're not told the charge of Q4. Regardless, you are asked to find the possible direction for the net electric field vector on, sorry, this should be Q, not G, Q4. So Using the very last slide that we just did, so using vector summation, find the total electric field vector on Q4, and I'll re-release the poll now. And if you guys can't see the poll for whatever reason, you can put your answer in the chat box. Yeah, I see your answer, Brian. Does anyone want more time? Okay, I'll just wait a couple seconds. Right, so you guys did great. That is the answer, D. And here is just a picture that shows how to arrive at that answer. So I didn't know the charge of Q4, but I assumed it was -1 because I knew the answer, and that was easier to show. But you can, it's not going to be so much more work just to also do that for the to do that if you thought that it was, that if Q4 was a positive charge as well. So anyway, this arrow shows the electric field that Q4 experiences for in relation to the positive source charge Q1, and this is for Q2, and then Q3. So the X, it's called the X vector, X component vectors for Q1 and Q2 cancel out. So all that's left is the Y components, and those are also pointing upwards. And Q3's electric field vector is also pointing upwards. So your final answer is a vector that is pointing upwards. Okay, it seems like you guys did pretty well on that, so I'll just move on. Just another question. Let me. So here you have two charged particles, and it says, assume that the direction of F is in the same direction as the electric field between R and S. If an electron were placed midway between R and S, the resultant force on the electron would be in which directions? So let me relaunch the poll. Give me 1 second, Alika, sorry if I said that wrong. I'll go back to that question after we finish answering this one. I'll give you like 15 more seconds. So we are evenly split between A and B, and then Brian also said. And so the answer is actually towards S. And the way to think about this is that the first sentence basically is a complicated way to say that the electric field line points towards R. And if you remember that electric field lines by convention show the direction that a positive charge would feel attraction towards, that should be the hint that because you're talking about it, if that was the case for an electron, and an electron is a negatively charged particle, it would face a force that is in the opposite direction of the electric field line. So because a positive test charge would feel an attraction towards R as indicated by the direction of the electric field line, a negatively charged particle, such as an electron, would feel an attraction or attractive force towards S instead. Is that explanation okay for you guys? It seems to be a little bit more confusing. Okay, great. Thank you for responding. So I'm just going to go back to the previous question for a second. So you said, shouldn't the arrows be going away from the positive and towards Q4 since it's negative? Let me know if I'm interpreting your question wrong. And also please say your name so I can say it right. But if you want to unmute yourself, if that's okay. Alika, are you here? Okay, no worries. So I think you're asking why we figured out that Q4 is a negatively charged particle, so shouldn't the arrows be facing, the electric field line should be facing towards Q4? Okay, yeah, that's that's a mistake in interpreting the question. So in this case, we're trying to find out how the other particles are influencing Q4. So if you remember our discussion on source charges and test charges, here we're designating Q4 as a test charge. So the way the question is asked, Q1, Q2, and Q3 are the charged particles that are generating the electric field lines. Sorry, just 1 second. Sorry about that. Got distracted. So Q4 is our test charge, and then we have Q1, Q2, and Q3 as our source charges. So it's asking you, if Q4 is our test charge, what is the direction of electric field line? What is the direction that its electric field would be in relation to the other charges? So we didn't know initially if that was a negative test charge or a positive test charge, but this diagram is assuming that it's a negative test charge. And once we know that it's a negative test charge, we can relate that negative particle to the positive particle. Okay, you can go ahead and unmute yourself, Brian. Thank you.
I think for this question, actually, we don't even need to apply the concept of electric, since this is just a vector and the vector can be canceled out. The vector for Q1 and Q2 is exactly opposite, same magnitude, but opposite in direction. So the only vector that's left is Q3. And that's why this is pointing upward.
Yeah, that's true. But I think that maybe what she was asking, or sorry, what they were asking is that why is that vector even facing in that direction to begin with? So it essentially comes down to the fact that negative particles are attracted to positive particles. So that's why the electric, the electric field lines face that way. I don't know if that helped. That was a very confusing way to put it. Is that okay? Okay. Sorry about that. Let me just give me 1 second. Okay, sorry, I'm back. Does anyone have any questions in general before we move on to the next half? All right, so the next concept we have is this concept of electric potential energy. So this again relates a property when you have two charged particles. So if you think about it, electrostatic force talks about the property between two charged particles. And that's why in the equation you have Q1 and Q2. On the other hand, the electric field is an intrinsic property of any one charged particle. So in the equation for electric field, you only have one Q, so one charged particle. So electric potential energy in that regards is more similar to electrostatic energy in that you're talking about the relationship between two charged particles. So while electrostatic force talks about how, or is a way to calculate the force between two charged particles, electric potential energy is an equation to calculate the potential energy between two charged particles. So another way to think about this is that because the electric field is also created by a charged particle, sorry, let me back up. So I said that the other way around. So I described electric potential energy as energy between two charged particles. However, with any two charged particles, one particle will be creating that electric field and the other particle will be feeling it. So another way to define electric potential energy is the potential energy of a charged particle in an electric field created by another charged particles. So the electric potential energy, if you look at the equation on the right, it depends on the position between the two charged particles as well as the magnitude of the charges of the two particles. So if you try to relate this to the other two equations, here, if you like cut off this test charge, actually, let's not do that just yet. I'll decide on that later. Sorry about that. So to relate this to like and unlike charges, if charges have opposite sign, electric potential energy becomes negative. If the charges are of the same type, so if they're positive, your electric potential energy will be positive. If they are negative, electric potential energy will be positive also. So what this means is that if your electric potential energy is positive, so if you're calculating electric potential energy between two like particles, then electric potential energy is inversely proportional to the distance d. So this means that the farther you get away, the lower the electric potential energy. So this makes sense because electric potential energy is like the energy that two particles have to either get closer to each other or farther away from each other. So when you have two like particles, they are their natural instinct is to move away from each other. That's why the energy to move decreases the farther they get apart because they like being apart. On the other hand, if electric potential energy is negative, so this is between two unlike particles, electric potential energy is directly proportional to the distance d, which means that electric potential energy increases as they get farther apart because that is an unfavorable state for them. They have this additional energy now that they're farther apart because they want to move closer together. Okay, so that was the end of electric potential energy. So this is our final concept that we have to deal with equations for today. So this is electric potential. So this is like more like an electric field. So electric potential energy and electrostatic force. You talked about the property between, those are properties that exist between two charged particles. Electric potential expresses the effect of the electric field caused by a source charge in terms of the location within that electric field. So this is an intrinsic property of that electric field generated by a single charge. So electric potential energy can also just be defined as the electric potential can be defined as electric potential energy divided by a charge of the test particle. So electric potential energy can be defined as the electric potential energy per unit charge. So this is a scalar quantity, and it is, as this image says, it's purely dependent on the location within the electric field. And the notation for electric potential is V. And the units are joules per coulomb, which is the same thing as volts. So again, to keep reiterating, well, electrostatic energy, which is the same thing as electric potential energy, depends on the position and value of the test charge. The electric potential only depends on the position that you're calculating in the electric field. So this is, again, a convention. So positive test charges will move spontaneously from high potential to low potential, whereas negative test charges will move spontaneously from low potential to high potential. So if you think about two electrodes and you have a positively charged surface and a negatively charged surface, negatively charged test particles will be attracted to the positively charged surface, and positive test charges will be attracted to the negatively charged surface. As a result, the convention that is arbitrarily designated is that positively charged electrodes are of higher potential than negatively charged electrodes. So what you might see in questions is that you'll be shown the electric potential direction of negative test charges or positive test charges, and they won't label these electrodes for you, and you should be able to identify which is the higher potential electrode based on these directions. Look at the chat, we have a couple questions. Can you clarify? Yeah, so this is what I was trying to explain that is arbitrarily defined. So it's not like an existing property in nature. We just define the position that negative test charges move to as being of higher potential. So it's kind of an arbitrary designation by convention.
So we don't use the positive charge source or negative charge source as something to indicate. We're using the flow of the electron arrow to indicate if this point to the higher or pointed to the lower. Is that correct?
What do you mean by that? Sorry.
Are we identify the potential whether it's higher or lower by the arrow of the charge?
Yeah, I was just using that as an example. Like that might be a question type that you'll see. So I was saying that if you have a direction of current or direction of electron flow, and you might be asked what is a higher potential surface given that electric potential.
Does it matter which way has more positive charge?
Like, do you mean?
On this slide, we are showing the top is more positive, and the bottom has a lot of negative charge.
Mm-hmm.
But I was wondering, when they mean higher or higher in potential, do they mean like if there is more positive charge on one side, and then it will be indicated as more positive.
Yeah.
As
So,
more potential.
yeah, that's how we define it. So if the position that has more positive charge is defined as being higher potential. And it doesn't
Okay, thank you.
intrinsically have any meaning, but that's the meaning that has been assigned to it.
Mm-hmm.
Okay.
I understand now. Thank you.
Okay.
Mm-hmm. Yes.
Okay. Thank you for asking. So here's a slide summarizing the four equations that we looked at so far. So these are the two equations that are intrinsic to one charged particle. So you have electric field, and that's kq over r squared, and electric potential is kq over r. And then these two equations, electrostatic force and electric potential energy, are qualities that define characteristics between two charged particles. So that's K for electrostatic force, that's K, Q1, Q2, or you can also write it this way, but same meaning, divided by r squared. For electric potential energy, that's K, Q1, Q2 over r. So this, I think, is more like a memorization tool than anything, but you can go from electric field to electric potential by multiplying by R. Same thing, you can go from electrostatic force to electric potential energy by multiplying by R. And this, in this direction, you can go from electric field to electrostatic force by multiplying by Q, and then electric potential to electric potential energy by multiplying by Q. A couple more quick concepts. Equal potential lines are lines along which the electric potential is the same, and they're perpendicular to the electric field lines. So these black lines are your electric field lines. So they have different electric potential along them. And these equipotential lines are lines that have same potential. So at this point on the equipotential line, the electric potential is the same as this line. Same thing. So if these black lines indicate electric field, these red circles indicate that all along this red circle is the same electric potential. Same thing along the smaller circles. So we look at these electric equipotential lines to basically define that you don't need to do work to move a charge along this equipotential line, because there's no difference in electric potential. You don't need to know a whole lot about this aside from the fact that perpendicular to electric field lines and that no work is needed to move a charge along an equipotential line. Another quick concept is electric dipole. So a dipole is a separation between a positive and a negative charge by a certain distance. So when you place a dipole in an electric field, it faces a torque until it is aligned with the electric field. So the positive end will be in the direction of the electric field, and this fits along with the concept that we're talking about. Electric field lines are designated such that we think about a positive test charge being dropped into that electric field. So as a result, similarly, when you have a dipole, the positive side of the dipole will face along the direction of the electric field. To summarize, because I know a lot of this sounds really confusing, I had to keep myself straight a lot of times when I was putting together this topic session. So keep practicing with this until you get a hang of it, but I'll try to summarize this for you as clearly as possible. So the electrostatic force is the force that exists between any two charged particles. On the other hand, an electric field is a charged field that is generated by any one charged particle. This field is the thing that exerts an electrostatic force on any charged objects that enters into the space of that electric field. Sorry, Electric potential energy, on the other hand, is the energy that charged particles have because of their own electric charge and their relative position to other charged particles. Lastly, electric potential is the electric potential energy per unit charge and is an intrinsic property of the electric field of any given charged particles. And the electric potential depends only on the location um, in the electric field as well as the charge of the source charged particle as well as, of course. So this is just a summary of equations that are used for electrostatic statistics. We didn't cover all of this yet because that will be in an upcoming session on circuits, but you can use these equations to memorize